Welcome to the E4S for ECP ST and AD teams. I hope you are able to see my screen here.
Yep.
And we will be having a hands-on session on AWS instances. And to sign up for one of those instances, you'll have to go to this URL, e4s.io/tutorial. Let me just put that in the chat window. You can sign up for an instance over there. We'll wait for another minute or so for people to join in. And this tutorial is meant for our ECP ST AD teams who are trying to get a better sense of what E4S is, what technologies it presents, and how they can make more effective use for it. I hope you are able to sign up for an instance and launch a remote desktop session for an instance on AWS. There is a README file, and we'll go through some of the examples there after the slides are done. But before we start, do we have any questions? Okay, great. I hope you are able to access the URL that I just posted in the chat window. I will be monitoring for questions. So the key challenge that we are trying to address here is that as our software gets more complex, it's now getting harder and harder to install our tools, our libraries, our applications correctly in an integrated and interoperable software stack. And to address that problem, we have the extreme scale scientific software stack, which is a curated Spack-based software distribution of not only HPC, but also AI and ML packages. And it includes support for GPUs. It includes support for Intel OneMPI, NVIDIA's NVHPC, AMD's ROCm, and is a full software stack that is built with support for GPUs from ground up. It features binary build caches as well as containers to help you get started and install the tools and libraries quickly and be more productive. You can find out more about E4S from our e4s.io webpage. And there are binary build caches that we have where you can install packages more easily without recompiling from source code. And we have support for x86-64, PPC64LE, and ARM64 or AR64 architectures. So E4S has container images which are available on Docker Hub as well as on the E4S webpage. And these container images have pre-built binaries of ECP ST products and other tools and libraries as well. We have a range of containers. In fact, we have support for GPUs from all the three vendors. And we have base images that you can use to customize your own image. And we also have full-featured containers as a reference implementation that supports all the GPUs. We also have GitHub recipes for creating custom images from the base images. So you have a range of choices with this package. We have a integration with GitLab. We have a validation test suite, which is available on GitHub. And we also have a container launch tool. This container launch tool is a very interesting package that allows you to launch our containers on a range of HPC systems. And it allows you to substitute the MPI that's there in the application with the system MPI. And it supports MPICH, it supports OpenMPI, And I'll give you an example of using it. We also have a VirtualBox image with support for different container runtimes if you're getting started with containers, and also the AWS images that you'll be using. So there are three main focus areas, as you already know: the application development, software technology, hardware and integration. And the software technology area has over 70 unique products that span various areas such as programming models and runtimes, math libraries, data and visualization. And we have taken products from this ST area and other commonly used products and integrated them in this extreme scale scientific software stack. Here is our roadmap to exascale systems. As you know, that until now we had GPUs from only one vendor, NVIDIA, in the Summit and Sierra systems. And going forward, we have GPUs from 3 different vendors in our upcoming systems, such as Frontier and LCAP, and Argonne's Aurora system, and of course the Perlmutter system that's already operational at Berkeley Lab. So our goal is to build a comprehensive, coherent software stack that enables application developers to be productive and to develop highly parallel applications that can effectively target these architectures. We want to prepare a software stack for scalability with massive on-node parallelism. And you may have seen our products such as Cocos and Raja that are used extensively to address that need for massive on-node parallelism and to be able to write performance portable code that can target these GPU architectures. We want to extend existing capabilities when possible and develop new when this is not possible. We want to guide and complement and integrate with vendor efforts. We want to develop and deliver high quality and robust software products. So these are very interesting goals that we have, and there are many technical areas that ECP ST spans, including a newly integrated area for ExaWorks for workflows. So you may have already seen that these technical areas span programming models and runtime, and this includes MPICH, OpenMPI, tools that you're already familiar with. It includes Cocos, it includes Raja for on-node parallelism. We have development tools, which includes performance evaluation tools such as PAPI, Tau, HPC Toolkit. It includes LLVM compilers. We have math libraries, a range of packages that come here, including PETC, Trilinos, Sundials, SuperLU, data and visualization packages, software ecosystem, and even NNSA ST tools. And we work on products that the applications teams need now and into the future. And these are some tools that you are already quite familiar with, such as MPICH, OpenMPI. There are tools like PETC, Trilinos, and then there are other tools for on-node parallelism, such as Cocos and Raja. These are provided through the Spack package manager. And then there are new tools that we are developing. This includes SICM, that is the simple interface for complex memory hierarchies, the ZFP, Unify, CR, and you can see examples of these products over here, including LLVM and vendor compilers, performance evaluation tools, math libraries, IO packages, and data and viz tools as well. And these products are integrated through the software development kits or SDKs into the E4S distribution. And then we have the integration and the delivery of these products. So our goal in E4S is to provide better quality software with documentation, tests, and integration, and to have a common framework for all of these. We have community policies. We have a doc portal, which is a single portal for all the E4S product information. We have portfolio testing. It's a curated collection with quarterly releases. We recently had a release in February, the 22.02 release, and build caches that can help you improve the time for installing the packages. We also have a strategy group that comprises US agencies, industry, and international partners. So if you go to the web page for E4S, E4S.io, you can see the policies right here on our web page. And these are common sense community policies. They have been developed together with feedback from the HPC community. And these are policies such as to be a member package in E4S, you should have a Spack package. So you should have a recipe. We should be able to install your tool through Spack. It should have some minimum validation testing, and these test suite integration will allow us to ensure that the package is doing what it claims to provide as its features. It should have documentation. There should be an entry in the E4S doc portal and a range of other policies like this, including error handling, test suite, and so on. So these have been modeled after the XSDK community policies. You can learn more about these on our webpage. And starting with the first release of E4S that happened in October 2018, where we had 24 packages. Now we have in 22.02 100 full release products, and I'll show you examples of what packages we have. And besides the products that I describe here that are installed using Spack, we also have other products in our containerized distribution. These include commonly used products for AI community, including PyTorch and TensorFlow, with support for GPUs. Now, you may find that it's rather cumbersome to install TensorFlow or PyTorch with support for, say, the AMD GPU or the NVIDIA A100 GPU, but these are already integrated. There are other co-design packages like Amrex, Kibana, MFEM that are part of this release. And we base our distribution on the Spack package manager for software delivery. Spack allows us to install different packages. It also allows us to install the same package with different versions and configure this package in multiple ways using different variants or options that are provided by the recipe of that package. And it's a build layer for not just the E4S software, but also a large collection of other tools and libraries outside of the ECP software technology area. It supports achieving and maintaining interoperability between the ST software packages. And you can learn more about it at the Spack.io webpage. And the motivation for using Spack is quite simple. Our software is becoming extremely complex. Here is the dependency graph of NALU, a generalized, unstructured, massively parallel low Mach flow application. It's used for wind turbine simulation or the near body simulation using the CFD package. And you can see that NALU depends on Trilinos, it depends on Parmetis, which depends on Metis, it depends on SuperLU, NetCDF, and a range of packages that all need to be installed in a consistent manner using the same software stack, using the same MPI library for it to operate correctly. Here is Deal2, a C++ finite element library whose dependency graph is even more complex, as you can see here. And this is the complex graph of RMiner. So you get the idea, our tools are getting more and more complex. We need to have a good way to install the packages. And even the proprietary codes are based on many open source libraries. You can see the DAG over here, which is in blue, represents open source packages. And nearly all of it needs to be built specially for HPC to get the best performance. And we are actually building an entire ecosystem of products, including more than 15 applications, software packages for multiple target architectures, for different compilers, programming models, and different versions of each package. And it leads to a combinatorial explosion. I have a question here about building E4S for different GPU architectures. And yes, we target multiple GPU architectures within the same release. So even a single release of E4S can have support for V100 GPUs, which is the Arch equals 70, SM70, as well as the A100 GPUs for NVIDIA, which is the SM Arch or CUDA Arch equals 80. And we also have support for multiple GPUs for AMD. For instance, we have support for GFX 908 or the MI100 platform, as well as GFX 90A or the MI250X within the same 22.02 release. So we have packages built for multiple of those combinations. And you can see that with that complexity comes the increasing number of target architectures, even within the GPU architecture. The same goes for the Intel GPUs, which include, say, DG1 or the Tiger Lake platform, which supports OpenMPI. So does that answer your question, Cameron? And will E4S be required? Okay, good. Will E4S be required for or only encouraged for shared applications on the exascale systems? Well, we do plan to have E4S required and installed on the exascale systems, and it will be available as modules that the applications teams can use. It will be installed with Spack, and the ST packages will be available through this this distribution. I hope that answers your question, Donnie.
Yeah, I just wasn't sure if available means that it will be the standard for all the installed applications, or if it's just a choice.
So the vendors provide their vendor stacks, as well as the E4S will be available with each new version on the exascale systems and updated periodically. And the applications teams can, of course, build their own stack in their own project areas, but we encourage them to use the products that are available from the E4S distribution, which will support, say, the ProgEnv, Cray, AMD, NVIDIA, and so on, so that they are able to access all the packages in a consistent manner and have access to the packages that use MPI, that is GPU aware, that works with Slurm, that uses the slingshot interconnects effectively, and so that they have a full distribution of tools and libraries that they can readily access with the compilers of interest to them and build their applications using this E4S. Does that help answer your question?
Yes, thank you.
Great. So as you can see that to build an application is a complex process, especially as it targets multiple architectures and different programming models and versions. And now the situation has gotten to a point where facilities are dedicating many FTEs just for porting and building of applications. And they often trade reuse and usability for performance. And we must make it easier to rely on other people's software. But how do we install software on a supercomputer? First, we start off by downloading all of the tarballs that we need. And how does that look like? We download these tarballs and we start building. And this is a complex process where we configure, we use make, We fight with the compilers, we tweak configuration arguments, we configure again. And finally, when all these 16 tarballs that you need for your application are installed, then we integrate it, then we build the code, we get a binary, we run it, it may seg fault, then we start all over again. And there has to be a better way. And you may say, well, what about modules? Why can't I just use modules? Well, modules are just wrappers. Modules are just setting environment variables like path, LD library path, and someone else, likely a team of people, have already installed the package, and the modules are just providing the interface to that package. And Spack also creates modules that you can use if you prefer not to use the Spack commands. And it's actually very simple to use Spack. All you need to do is clone the Git repo of Spack like this and just source an environment variable file, set up env.sh, and then you're ready to install packages. You can say Spack install tau, and then tau and all its dependencies are installed within the Spack directory hierarchy. And I encourage 2 additional steps. One is the Spack compiler find, so that you don't have to install the compilers as well from Spack, and you can just use the compilers that are already in your path. And it will find compilers like GCC at 9.3.0, and then it will have the compiler definition updated. You can also say Spack external find. So it will find external packages like M4, AutoConf, and other packages. And then you can say Spack install tau or tau version 231. And you can see that you can specify GCC compilers like 930. And you can turn on variants like plus Rockham. And you can say plus MPI and specify the flags for MPI, such as MPICH 2, version 2.3 without the wrapper R path dependency. And so you can specify in great detail how a package should be installed, with which compiler, with which flags, and then you can see exactly what is installed. And here is, for example, Trilinos installed in the set of packages. So Spack is central to ECP's software strategy, and it enables software reuse for developers and users. And you can learn more about Spack from the spack.io webpage. And Mike had a very interesting comment. He said that I don't see that all apps will access libraries and tools through E4S. E4S builds versions of its member products that are from stable branches. If an application is working closely with an ST team, it's probably using a version of the product that's under development and not integrated into E4S at that time. This kind of feature development lifecycle is natural when we have app teams working with the ST libraries and tools teams. New features will make it into E4S as they get stabilized for broad distribution. And that's true with our quarterly releases. We'll get the stable versions in there. And for apps that don't need the bleeding edge features, accessing the tools and libraries through E4S makes good sense. Excellent point. Yes, you can have a E4S installation on a HPC site and use the stable releases of all these packages available through Spack on bare metal as well as through containerized distributions. Mike, did you have some other comments?
That wasn't me. I'm not sure who spoke up.
Yeah, that was Victor, I think.
Was there a question?
I guess not.
Okay.
I guess we can continue. And the software development kits that comprise all these products, you can look at a set of applications. Now, let's look at 5 different applications. The EXA wind turbine wind plant efficiency code from NREL, the subsurface code, which is used for carbon capture, fossil fuel extraction, waste disposal from Berkeley Lab, the WDM app for the whole device modeling, for the high fidelity whole device modeling of magnetically confined fusion plasmas, for the ITER reactor from PPPL, and the EXA-SKY, the cosmological probe of the standard model of particle physics, and the MARBLE multiphysics codes. EXA-SKY is from Argonne National Labs, and MARBLE is from Lawrence Livermore National Labs. And you can see that these applications use a range of products from E4S. They could be products like MPI or Tau or Raja or Strumpack, SuperLU, Trilinos, Alpine, MPIIO, you get the idea. And all of these are products that span multiple areas. And you can see how the software development kits that group logically related products into these areas, such as PMR core for programming models and runtime, or compilers and support, tools and technology, or XSDK or Math SDK, are all represented over here. And Cameron asks a good question, that is there a trade-off between containerized deployment when compared to bare metal installation? Are they functionally equivalent? And yes, they are functionally equivalent. And there may be a slight performance difference between a containerized distribution and the bare metal installation. In fact, in some cases, they have found that if you're using Python and you're using a large number of shared objects, then a containerized distribution may actually be faster than a bare metal installation, because the metadata transfers that take place come from within the containerized distribution and do not need to go through the Lustre file system in many cases. And that may lead to some efficiency gains in using the containers. And we can also replace the MPI in the application with the system MPI. So you can have a workflow that resembles the bare metal workflow as well. So there are some distinct advantages to using a containerized approach, and we'll cover that in the hands-on session.
Great, thank you.
Here is how we develop the distribution comprising of multiple SDKs, where we have to, we develop the we package it, we build it, test it, and deploy it, and then multiple of these SDKs are then integrated and built and tested and deployed on the bare metal platforms. So to answer your question about containers, what is a container? Now, you may have heard of Docker container. Well, containers provide a lightweight collection of executable software that encapsulates everything that is needed to run a single specific task without the operating system kernel, and it's based on Linux. And Docker is a very popular container runtime, and it's available on all major platforms, widely used in industry. And you can think of it as, if I want to nail down all my dependencies and create a container that will be available to me and will work even if the operating system underneath the container changes and there are updates to the system and the compilers and the OS changes, as it does frequently on our HPC systems. How can I get a consistent software stack that will be sort of frozen in time and that I can rely on to get my workflow done without worrying about the changes that may happen to the underlying system? Then containers do provide a viable way to reproduce your scientific results. And the key difference there is that if you look at these three scenarios, where I have a hypervisor running directly on a hardware, where there's a full operating system in a virtual machine running on top of a hypervisor, or a hypervisor running on top of another operating system where there's kernel running here in the VM as well as a kernel running here in the OS, then that's a big overhead, so to say. And with a container-based distribution, it's running on the host operating system. There is no kernel inside the container. So it uses the kernel of the operating system, and these are just libraries and the applications that layer on top of the operating system of the host. So there is some efficiency over here in using a container. And if you go to the E4S web page, you will see that there are a number of images. There is a minimal Spack image available for IBM as well as Intel architectures. And there are mirrors and there's Docker images, which have nothing but Spack and the Klingo concretizer and the compilers and build systems like Make and CMake. But there's nothing else. So it's a very lightweight container. And then we have GPU base images for NVIDIA, for AMD, for Intel. And you can see that for NVIDIA, we support not just x86-64, but also IBM Power 9 ARCH PPC64LE, as well as the ARM64 ARCH64 systems with CUDA. And you can start with a base image and add packages to it, and then you can have a full distribution. We also have continuous integration images for RHEL 7 and 8 and Ubuntu. And you can see these are the GPU runtimes that we support. Here is the minimal package, and it's widely adopted by the Linux community, not just with the HPC community. It has over 1 million downloads already. And you can see that it's available for x86, 64, and IBM systems. We have a Singularity image, and Singularity is a very popular container runtime that's available. It's very secure, and in its new version, Aptainer, it comes from scilabs.io, and it's available on many HPC systems. NERSC uses Shifter, which is another popular HPC runtime. So we have support for Shifter, Singularity, Charlie Cloud, and these base images that we provide, a full-featured base image, has support for GPUs from all 3 vendors for x86-64. So you can take the same Singularity image and run it on an Intel GPU or AMD GPU or NVIDIA GPU with, of course, different runtimes. And we have support for base images for IBM and ARM as well. There are some packages that support all the 3 GPU runtimes. And this is how it looks like. If you download the Singularity image, you can see that there are 100 different packages that are installed using Spack. And this is the exact location. You can see the DPC++ compiler, which comes from OpenMPI, is installed here. The HipCC compiler from ROCm 452, the CUDA package 1142, or the NVHPC package. They're all there in the same Singularity container. There are very popular tools that are available. You can see Amrex is installed over here. You have Ginkgo, you have GasNet, you have LAMPS, Cocos kernels, MPICH, you have OpenMPI, PAPI, Tau, tools like Trilinos, and you can see there are 100 different packages. We also have Julia and Python languages. Julia is becoming very popular, and there are AI products with support for GPUs, including TensorFlow and PyTorch. We have 3D visualization support in the Singularity container built in with ParaView, Visit, and Tau's Paraprof. And these are the packages for IBM Power 9 or PPC64LE. And you can see Arborex, Amrex, Conduit, and these are the directories: HPC Toolkit, Cocos, MPICH. And again, you have the AI products as well. So you can just use these containers. Here's Petsy, Raja, Tau, Trilinos, and so on. There are 100 different products over here. And you can also use this with Docker directly. You can say Docker pull and get this image, and you can get started. In fact, many of us use Linux and Mac OS in our laptops. You can install this image right on your laptop, and you'll have the full environment that you typically expect from an HPC system with MPI and Cocos and TensorFlow and PyTorch all pre-installed on your system. How does that look like? You can just say Docker pull, and you can get an image like this. On my own laptop, I can say Docker images. And here is an image that I had just done a pull on. I had said Docker pull ECP E4S / E4S GPU with 22.02, or by default, it will get the latest. And once you do this pull command, it will install this like this. And so then you can say Docker run and say --rm with the IT, and then give the name of this image and the tag like this. And with this, you will be able to just run the Docker container on your own laptop, and then get access to all of these packages. So if I said which HipCC, it's right there. Which MPICC, Spack find, and you'll see all of these packages available to you. And also through the module avail system. So you can say module load. So if I wanted to use Julia on my Mac, I could just say module load Julia, and I would have that package available to me like that. So you get the idea. You can use Python, you can use Conda and Spack. You can say opt intel one API set vars.sh if you wanted to use this, and then you'll have dpcpp in your path. You can look for NVHPC. You can see the tools from there. And you can build your applications right on your laptop, and then you can transfer them to the HPC site and then use our container launch tool to substitute the MPI, which is built into the application, with the system MPI. So you can get near bare metal performance as well. And I'll show an example of this as we look at the hands-on session and go from there. But are there any questions so far with what we've just covered with Singularity and Docker images? Okay, let's move on. So these are GPU images that are available. This is 22.02 full-featured image that I just showed you running on my laptop. And I can just say Docker pull like this. I'll of course have to install the Docker from the docker.com. And then I can run the container. If I had to use an NVIDIA GPU, I will say Singularity run with the --NV option so that I can have access to the NVIDIA, or it could be --ROCm for AMD GPUs. And here I'm seeing the configurations of Tau, which are built with kubectl support for the CUDA profiling tools interface. I can say Spack find the packages that have CUDA enabled in their variant, and where the CUDA architecture is 80 or 70. And you can see all of these packages that are built with different architecture specified as 80 or 70. So Cameron, this is a question you had asked about the building for multiple GPU architectures within the same distribution. And so you can see that. And you can say Python, where you say, conda activate CUDA or ROCm, and then you can have the TensorFlow, PyTorch. You can access the GPU like this, and you can see the A100 is being accessed. This is the bare metal Spack installation environment on GitHub. And this is the Spack.yaml recipe that ships with the container. And every container has this. Like in this case, I can see Spack.yaml. It's right here. And you can see how it was configured and how this container was built. So you can create your own custom image. You can create your own recipes using different options. These are the options used for the MI250X for the AMD GPU on systems like Crusher at Oak Ridge National Labs, or GFX 908 or CUDA 80, and you can see how the architecture is specified in the Spack.yaml file and for the different CPU options. And you can create your own custom Spack.yaml. You can cherry pick the packages that you want, and then you can just install it using spack-e.install after you make those changes. Okay, so this is the recipe for creating the Spack-based builds. And you can see the products built for the A100 or the MI100 and 250X, and those built with OpenMPI. Now, to speed up your installations, we also have a build cache. And here we have over 80,000 binaries in this Spack build cache. And there is no need to rebuild this package from the source code when it's downloading it directly with this build cache. You just have to add this mirror and say that Spack mirror add E4S, and then specify the build cache keys. And then you can use this build cache to install the packages. Here is an AWS image, and we'll use this for our hands-on. For those who just joined us and would like to get one of the images that we have booted up, I'm putting the URL, the e4s.io/tutorial, which has a key description of how you can pick an instance, and then we'll do some examples over there. And we also have a virtual box image. So this is the tool that is very interesting. It allows you to simplify the launch of MPI jobs in E4S containers. And we can replace the MPI that's built with the MPI libraries in the container with the system MPI. You can use MPICH variants such as MPICH2, Intel MPI, Cray MPICH, or even OpenMPI using the Wi4MPI tool that's installed in the AWS image. And this tool comes from CEA in France that allows us to interoperate between different MPI versions. And you can then build the application on your laptop, and you can literally transfer it to the HPC side and then replace the MPI with the system MPI. And this is how it works. You have to first pull in the MPI that you're interested in, and you have to specify 3 things. What are those 3 things? You have to say which backend to target. So you can say it can be Singularity, or it can be Docker, or it can be Shifter. You can specify the container image, the Singularity image, which I have specified here. And then also specify what needs to happen when that image is loaded. Which package do you want to load? A package like Trilinos, which version of that, and so on. And with this, it will figure out for the MPI that's loaded in the environment, which libraries need to be put in which order. So you don't have to do that yourself. You don't have to worry about mounting certain file systems from the MPI into the container. You can just say E4SCL, srun, or MPI run, and ADOL out, and then it will do the right thing in substitution, and then it will allow you to run your code. it sounds very difficult or challenging, but we will actually see this in action on the AWS image that we have booted up. We have a hands-on session planned right after these slides. And this is the architecture of the E4S CL container launch tool. And here is an example of the multi-platform E4S Docker recipes that you can use. And this typically looks like this. A Docker file is created where you say, this is the starting image. You start from here, you copy things in this directory, and then you run this Spack install. And then this is the working directory. And when it creates a new image, you can then use that from the Docker image. And here are reproducible Docker recipes for different architectures. And some applications have been using the E4S build cache. We encourage the apps teams to consider working with us. Please get in touch with us. And we have an issue tracker, which allows you to specify support issues. And we would like to work with you and get E4S Spack build cache integration, container integration done for your applications. And we have a team at ParaTools, and many of our team members are attending this tutorial as well. Here is another example of an application that was WDM app. This is Pantheon, and they have reported 10x speedups in their build times, which can be very interesting for building codes on systems like Summit. But it's not enough to just install packages in a container or a bare metal system. We need to make sure that the packages are correctly installed. And so we have an extensive validation test suite that can allow us to sweep through a set of installed packages together and see that the whole collection is working correctly. And here is an example. Each directory of the validation tests has a clean.sh, a compile.sh, a setup.sh, a run.sh, and we can keep adding more tests to this for different packages. So in short, I would like to say that E4S is an open architecture software ecosystem that accepts contributions from US and international teams. It's extensible. It's a framework for collaborative open source product integration. You should not think of it as a closed system that only takes contributions from just DOE software development teams. And it's not a monolithic take it or leave it software behemoth, but rather a full collection of software capabilities and a manifest of a la carte selectable software capabilities where you can extend the distribution that is provided by E4S. You can cherry pick the packages that you want and then create a custom distribution for which suits your needs. It's not a commercial product. It's a vehicle for delivering high quality reusable software products in collaboration with others. It's not a simple packaging of existing software, but rather a conduit for future leading edge HPC software targeting scalable next generation computing platforms or exascale systems. And it's a hierarchical software framework to enhance software interoperability and quality expectations. It has emerged as a new top-level component in the DOE HPC community that enables fundamentally new relationships. And we are talking with other partner agencies in the US, with industry and international collaborators. NSF and UK are examples. It will expand to include new domains. We have already started looking at machine learning and AI with TensorFlow, PyTorch. We're looking at lower level components and other. It can provide better, faster, and cheaper, the three important parameters for software. Some of the work goes on at the Performance Research Laboratory at the University of Oregon in Eugene for E4S, and would like to thank our sponsors, the Exascale Computing Project, which has sponsored the E4S project. And for our hands-on, let's move on and reserve an AWS instance at this e4s.io/tutorial. And then if you pick up a host such as 23, then you will log into the HTTPS tut023.supercontainers.org/8443 port slash colon 8443 slash hash E4S, and then give the login name as tutorial and the password as HPC Linux 12 exclamation, and then look at the README file. And yes, we will actually create a container. We will use Docker as well as Singularity. We'll look at a full ECP application and do the hands-on session next. So again, start with this e4s.io/tutorial and reserve an instance, please. And let me just go and get a, here is the sign up sheet. Please pick one of these hosts and put in your name, email address. I have chosen, say, tut040, and there should be 40 instances. That should be plenty. So please put in over here. And then you can go to this HTTPS. Remember, you may have to press the space bar to get the login screen, and it looks a little bit like this. I have the, after logging in, I press the space bar, I enter the HPC Linux 12 exclamation, I click the unlock. And I can click on this GNOME terminal icon and get a screen like this. Okay, here is the README file that you can launch, or here. And in this, I will first go to the containers tutorial where we build a Docker and a Singularity container by going to the src demo containers. And if you have never used containers before, or you're a little worried about this workflow, don't be. It's all just scripted. All you have to do is use cut and paste. If you can cut and paste with this terminal window, you should be all set. I'll wait for a minute or two for everyone to catch up, and then we'll go to the src demo containers. This is in the README file, and src demo containers. What I'm going to do here is I'll start with a base image of E4S, a Docker image, and then I will add an MPI application called hello world.c to this app directory, starting with the Ubuntu 18.04 image, and then go to this directory, source my Spack setup.env, load the MPICH, compile it with MPICC, create an application executable in the container, and then package this up as another container, starting with the base image, which did not have this application. So here is the hello world.c, and all it does is say prints hello from this rank in this, on this system. So it's a simple MPI application. We want to start simple, but we want to build a container image with this. And there's a README file on how to do this. So this is the Docker file. And then we'll just have this one command for building. So again, let's just, I would encourage everyone to try and get an image, an instance on AWS. Just reserve one of these so that you have your own desktop. And If there are questions, please let me know. So this is the Docker image. And we start with the Docker file here. And you can see Ubuntu 18.04. This is the docker.io image. And what I'll do is I'll say Docker file. And with this, I'm saying pick up the image over here, add the simple hello world application, and load MPI, compile it, and put the executable in the /app directory. That's all. And to do that, all I have to do is say Docker build and give it a name, and then give it a directory where the Docker file is located. So here is the Docker build command. I'm saying the tag is my hello MPI and colon latest, or I could put a date or something here, and then the dot. Okay. So this is the command, Docker build my hello MPI latest dot. I am in the src demo directory. So if I launch the terminal, gnome terminal, cat the readme file, cd to the src demo containers directory, cat the readme file there. Okay, cat the Docker file, and then say Docker build -t my hello MPI latest dot. Dot means it will pick up the Docker file from the current directory. And this is how it looks. And that's it. It's done. It picked the image from this. It added the hello world over here. It used this cache. It created the new application. And there it is. It committed. And now you have my hello MPI latest as the container. So now I can say Docker run. Okay, I can say --rm -it and then give this my hello latest. And there it is. I am now in the Docker container. And here you can see if I say cat etc OS release, I'm in this Ubuntu container. And if I go to the app directory, I'll find my executable right there. So this is no different from taking, say, a Word document, adding a paragraph to it, and then saving the document again, where I started with a E4S base image. I added this application called Hello World. And then I created the executable for it in the recipe. And now I can say MPI run hello. And it will run it on 4 MPI ranks. So remember, I'm inside the container here. I'm in Ubuntu. If I exit from here, now I'm back on AWS and I can see etc OS release. And I'm on Amazon Linux here. And these are the commands that I typed on the container. Any questions so far in picking up a base image and then creating your own image with Docker? Okay. I hope more of you sign up for the instances. And here is the Singularity hello.def. This is how I create a Singularity container. I'm saying bootstrap with Docker, start with this Ubuntu image, latest. And you can see the full syntax of this over here. Here is a file, hello world.c. I am doing the Spack setup.env.sh. I'm loading the MPICH. I have the hello world.c here. I'm compiling it to hello. And then to test it, I use the Spack setup.env.sh. I do the Spack load, and then I run this on 4 CPUs. This is a run script. This is what happens when you run the container. I'm just doing an echo over here. I'm again loading up the Spack environment variable, loading up MPICH, and then running the application. So I wanted to start with something easy, allow you to create your own def file where you can have your own application. And you can start with a base image from ECP E4S like this, and then add your own application, create your custom container, and then run it like this. So this is a Singularity container, and I have a hello.sif file, which is the container image. And now you can look at the README file. I may delete this and create a new image. And to do that, all I have to say is the Singularity build. But I have to use sudo to do that. And when I use sudo, I should use my password. So let me just remove this hello.sif. And then I will just say sudo Singularity build hello.sif is the file that should be created, and start with hello.def. And then I can give the password, and it will build this image. It starts with hello world.c. It copies this blob. It creates the SIF file, the Singularity image format. So it's a simple command. You say Singularity build. This is the .sif, and then you have the hello.def. And then you should be able to get this image. Again, for those who are just joining us, you can go to the https e4s.io/tutorial webpage. Here you can reserve an instance. And then once you have an image instance, you can just connect to it with the instructions in this page, all in a web browser. Open up a GNOME terminal, and then cd to the src demo directory for containers like this, src demo containers, and then cat the readme file. And then you'll be able to create the image starting from a singularity.def file. Well, I'll stop here and see if there are some questions for the things that I showed here. We started with a Docker-based build like this, and then we ran it like this with the MPI application. Then we can also push this new image to Docker Hub if you have a login over there. And then we created a image with sudo singularity build like this, and it's building this image, and you can see the various output print statements. And there,
We've
it's
been
creating this.
successful original.
Pardon, would you please repeat that? Were you able to get a successful build? There is the hello.sif. This was the test. I can say Singularity run hello.sif that I just built. And
I was
this is
able to
the
get both images to build successfully. I had some error with the Singularity image. It just seemed to error out, but running it again seemed to work.
oh, good. And then you can see Singularity run hello.sif. It ran the hello, and the output that we put over here in the hello.def, right? So this just shows you that you can just take this hello world application, you can put it in the container, you can run it like this. Here is an echo statement that came out here. And all you have to say is Singularity run this. And you can start with something that's already that has MPI and compilers and other things in it. And then you can just put your application very easily into this container and then create your own Singularity file that you can post. And thank you, Mike. So I'll wait for a minute, see if there are any other questions. If you are able to try these steps of creating your own container. And with this, we'll go to the next part of using the main ECP E4S distribution container, which is in ECP.SIMG over here. And as you see, you have seen how to run the container. You just say Singularity run and the container name. And that's what we will do for our next part. Any other questions with the containers? Were you able to do the Docker file based build?
Samir, this is awesome. When I try to
Yes.
do Singularity run, actually, it can't find the Singularity command. Am I supposed to put something on the path or sudo or something?
Which Singularity? It should be in user local bin Singularity. Are you in the E4S image here?
Yes,
in
I
the web?
am on the tutorial website on the AWS image.
And which Singularity doesn't give you this? Try
Which
opening up.
Singularity? Yeah, it is there, actually.
It is there, right? Okay.
Yeah.
So then if you are in the src demo directory, do you see a hello.sif?
Okay, sorry, mistyped the command. My fault.
Okay. So you do have that, right? Singularity
yes, I do.
run
I'm sorry. Yeah.
hello.sif, something like
Typing
that. Okay, good. So let's go to an example where I have to build with Trilinos. Okay, there is an example called Zoltan. And to do that, I'll just say cd to Zoltan, and I'll say Singularity run with this ecp.simg in my home directory. So I'm in the Zoltan directory, but I'm saying Singularity run over here like this. Singularity run ECP.SIMG. This is the full image. It has Trilinos installed in it. It has one API. It has NVHPC, all of the packages. It has HipCC and the AMD ROCm stack. You can use it with the GPUs. So this is the full-featured image. And here I can say /clean.sh. Okay, I say clean.sh. It removes any executable that I may have previously built. And this is how we can load a package. I can say Spack load Trilinos 1301 built with the GCC compiler. So I can say compile.sh. And again, I say compile.sh like this. And it will take this cxx main.cpp file. It will pull in all of these libraries. You can see a whole bunch of these libraries are being linked in. These libraries come from the container. Okay. At the end, I will get an executable called Zoltan. Now, what is interesting here is I have MPI and Trilinos all from the container. What I'm trying to do is I will want to use this application with the system MPI on AWS. So I have this Zoltan application here. If I wanted to look at how many libraries it has, I could have just said Spack load like this, all within the Singularity container, and LDD on Zoltan, okay, to see which libraries it loads. Here is the Aztec OO. You can see the path to the Spack provided. MPI coming from MPICH 342. Okay, and all of these MPI libraries. How many libraries are there? It's loading 42 libraries. 42 libraries in the Zoltan, all coming from inside this container image. Okay. If I say Spack location -I Trilinos 13.0.1, it will show me the location of this directory where all these libraries are coming from in the lib directory. You see all these libraries here. Now let me just come out of the container. Yes, in Singularity, I have compiled it, and in Singularity, I just say exit. So now I'm back on the AWS. You can see that by saying OS release. I am on Amazon Linux 2. And I want to use this application. Now, if I say LDD Zoltan, you will see that, well, a whole bunch of these libraries that I had are not there on the host because they are there in the container, right? So what do I do to use the container with a different MPI? And this is where our E4S container launch tool comes in. Now, on the AWS system, I have several MPIs. I have OpenMPI, I have MPICH 2, AWS MPICH 2X, which uses the Elastic Fabric adapter of the AWS for low latency inter-node communication. I have Intel MPI installed over here, opt Intel 1 API. You can see over here. So I'm going to use all of those MPIs one by one and run the same executable. So I could say cat run E4S CL Intel MPI .sh. What I do here is I say E4S CL init, specify that this is a Singularity backend. Here is the image. And this is what I should do to load up the image. So I say source.sh. And this is very simple. All I'm doing is bringing up Spack and saying Spack load Trilinos 1301. This is what I need to do to get all the libraries in my path with the Spack. Just 2 lines of this saying just Singularity and ECP.simg after loading up the set vars.sh. I can confirm that this is the MPI from OpenMPI. And then I can run the code like this. So let's all do this. Just say run E4S CL Intel MPI.sh. And Cameron, yes, Spack command had changed. It no longer requires the -r for recursively loading Trilinos. It can just ignore the -r. Just an incompatibility between the Spack syntax that changed. But here is OpenMPI being loaded, initializing the OpenMPI environment. You can see the target launcher. This is the MPI run from OpenMPI. It found that it had to change 15 libraries. The 10 files that it needs to figure out how to load and put it in the right location with setting LD library path, and then mounting the libraries in the container image when it runs the MPI run command. So it does all that for you. You don't have to worry about anything. You just have to give it 3 things. First, what kind of container runtime are we talking about? Singularity. Where is the image located? Here. And what do you do to load the image before you run your application, which is the Spack load Trilinos command. And with this, now you can see that it's running the whole application, and it ran 2.83 seconds for ML so far. This is the same application that I could have built even on my own laptop. If I had to do this, I could have said -v $home with $home like this, and then I could have built this even on my own laptop at home. But you get the idea. Here is home users senior apps Trilinos Zoltan clean.sh. Okay, compile.sh. And I'm compiling with this MPICH on my laptop here. I get the Zoltan. I can say run.sh, and I can run it on my laptop here instead of, but it will run a lot slower. Let's try run MPICH 2. Say run E4S CL MPICH 2.sh. And here you can see it's running this on my laptop. It took 18 seconds here. So I do have the same executable. And then in the case of MPICH 2, you can see there are some other messages coming from MPICH 2 saying, this is the MPI run coming from MPICH 2X. It required 19 libraries. It's running this. It's much faster over here than on my laptop. Here it's just 3.19 seconds. And how did this look like? Run E4S CL MPICH 2.sh. And here you can see it's the same command, E4S CL init with the Singularity backend, image, source.sh, load the MPI command like that. And then there is the cat run E4S CL OpenMPI.sh. And yes, we can use the Wi4MPI package and then specify the same source.sh, ECP, and then say that the replacement goes from MPICH in the container to OpenMPI from to, and then run the E4S CL like this with OpenMPI. The same binary is being used with run E4S CL OpenMPI. And here Wi4MPI is turned on. And then you can see this is the Singularity, ECP.SIMG. And we will be able to run with OpenMPI. So we have Intel MPI, MPICH2, OpenMPI, all three different from the MPICH, which was there in the container where I ran it like this. This is on my laptop, and here it is, 3.7 seconds with OpenMPI.
Hey, Kiko.
Are there questions? Which E4SCL isn't finding the tool for me? Cameron, can you just do the run E4SCL MPICH2 or .sh? Does this work for you? It should be in the user local packages, E4S-CL.
So yeah, even that script doesn't work. Again, the which E4S CL just seems to not detect the tool. It doesn't show it anywhere in the path.
So it may be because you are still in the container. If you say cat etc OS release, does it say Amazon Linux or does it say Ubuntu? If it says Ubuntu, just type exit. And so you will be on the Amazon Linux. And then you will have all of these tools inside the Amazon Linux.
Okay, I see. Yeah, I had to be outside of the container in order to do that. Gotcha.
Yes, of course, because the host MPI is outside the container. Now, does it show E4SCL correctly?
Yes, I think so. Thank you.
Great. Anybody else have questions about running the container with 3 different MPIs using E4SCL? If this is okay, I'll go to the last part of this tutorial, which is Nalu Wind demo. And what we are going to do here is show you how we can use the build cache from E4S to create this Nalu Wind ECP application. And yes, we will run this application on this instance. We'll look at the output of this code. We'll look at the performance data from this code. You just have to do a CD to the Nalu Wind demo directory and cat demo.sh. Okay, you can just run this, but I'm going to do something even more interesting. I'm going to say Spack uninstall Nalu Wind. I'm going to start with deleting this Nalu Wind application. So I said a Spack uninstall Nalu Wind. And then, I should just type it here, Spack uninstall Nalu Wind. And then I'm saying spack-e dot install. So here is the spack.yaml for Nalu Wind. It shows you how to build it. and I'll say spack-e.install. What is interesting is I'm not compiling this Naluwind application from the source code. I'm installing it from the build cache. Do you see this? Fetching this file from build cache, Amazon Linux. So your application can be bundled as a blob, a binary that you can get from the build cache and install it instead of recompiling everything from the source code. And it could take a couple of hours to build everything from the source. If you were building all these different packages and the binary for Naluwind, and then you will have the Naluwind executable in your path. There it is. It's installed over here. And then I can just say demo.sh and run this. So demo.sh. And it's starting out with this. There's this CFD solver that's looking at these YAML files in that directory. And it will run it for 3 minutes or something like that. It takes a while. This is a full ECP application. And we are instrumenting it with Tau. We are going to look at the output. And you can see it's running at on all these CPUs. So we are getting the maximum benefit of the use of this AWS node right now, where it's running at 100% over here. Can you all try to do this? CD to the Naluwind demo directory, and if you don't, even if you don't uninstall it, just run the demo.sh, and you should be able to see in this directory, cat demo.sh. It's going to this demo directory, and then it will be writing out these files. You can see the output files getting created over here. There's no output.e yet. It will coalesce all of these 8 MPI rank outputs and create one output file, and even generate a Tau profile. So what do we learn from this? We learned that we can use E4S build caches to create our own applications binary and have an easy way to install it using the Spack build cache. We don't have to worry about recompiling everything from the source code. If you want to create an environment based on containers where we can nail down the dependencies, then it's easy to do that. We have a base image from E4S, and we can specify what we should add to the base image, create an application. We showed you how to do that with a Docker file. We showed you how to do that with a Singularity def file. And it's just a question of saying Singularity build with this def file, and then create the Singularity image file. And then you can run the Singularity image file to run your application. Here we are looking at a full application here for Naluwind, and we don't have enough time to cover all of this, but let me just say that you can run the code, then launch ParaView, view the output, and you can look at the README file for other examples. So we are at the bottom of the hour. Are there some other questions that you may have about this tutorial?
So I have a full question. -E to Spack install,
Yes.
install the environment in the current directory.
Yes.
Okay.
It just takes the spack.yaml from the current directory. That's the dot. And here I am in the output directory. I have the output.e. So I can say ParaView output.e to see what it did. And there's also a Tau profile.xml file that it creates. If you'd like to learn more about Tau, we have a tutorial at the top of the hour on the Tau performance system. You can attend that. Here is paraprof from tau, and I'm running tau profile.xml through that. So I'm looking paraview for the output of the code and paraprof for tau's profile. And then I'll launch the viewers this way. And I should be able to see the GUI tools and view the output. Here is tau's paraprof. It shows me exactly where the code is spending time. Here are 8. Here is the tau application. You can see the bellows total solve time. Here is the operation. This is using Cocos. And you can actually see exactly what the code is doing. And the time spent in the code. Okay, this is the Nalu. And you can see the low-level calls. Here is the output from the application. If I just say apply, and this is the paraview output. I can check the pressure, turbulent, viscosity, velocity. I can look for, say, the elements. I can look for point Gaussian. This is the output. Surface with edges. And look at the simulation as it goes through this. Look at the so you get the idea. This is the output and the performance data generated for the test we just ran. Here is the wireframe. So the image has the E4S has paraview, it has visit, it has tau, all part of this distribution. And then we can look at the output as well as the performance data. So with this, I'll end the session. Any other parting questions? I hope you got a good sense for what E4S can provide. And please get in touch with us if you would like any assistance with E4S. Any parting comments? Well, thank you for attending the E4S tutorial. And Earl, if you want to stop recording, that will be great.
Okay, I'm stopping now.